Hey, this is Horner, and we're going to look at the fluids book problems. This is from chapter 9 in your book. So it says, what is the average pressure on the soles of the feet of a standing 90-kilogram person due to the contact force with the floor? Each foot has a surface area of 0.02 meters squared. So they want the average pressure on the soles of the feet. So we know that we're going to have to multiply this area times 2 in order to get that number. But remember, pressure is really simple. It's just equal to force divided by unit area. The force of the person is just their weight, which is mg, divided by their area. Mass here is 90. Gravity we know is 10, acceleration due to gravity, and then we're going to have 2 times 0.02 because we have 2 feet. And then your final answer here is 22,500 pascals. Number 6, we have a lid on a box. It is 15 centimeters by 13 centimeters by 8 centimeters, and the box is evacuated, which means that they just remove the air until its inner pressure is about 0.8 times 10 to the 5th Pascal. So they're trying to remove a little bit of air here. How much force is required to lift the lid at sea level and then in Denver on a day when the atmospheric pressure is 67.5 kilopascals, which is about 2/3 of that here just at sea level. So for letter A, we know that pressure is equal to force per unit area. And so we can rearrange that equation and say it's equal to force is equal to the change in pressure times the area. The pressure that we'll use is 101 325. Here we'll just do 300 pascals. You could also do 1.013 times 10 to the 5th Pascal, same thing. And we're going to subtract off the change in pressure, which is 0.8 times 10 to the 5th pascals. So that's what the inner pressure is. So outer pressure, inner pressure times the area, which is 0.15 times 0.13. And so when you do your math, you should end up with about 420 newtons of force. For letter B, if you took this can to Denver, then it'd be 2/3 of atmospheric pressure, which is 1.013 times 10 to the 5th. So that's the other way to write this number. And that number is about 0.6753 times 10 to the 5th. Well, just by glancing at this number and then looking at the number of the pressure on the inside of the can, actually it's got more pressure on the inside than it does on the outside of the can. So there is no force needed. No force needed to open the can. Just really easy can to open. Just barely pop it and it goes. Next one is a little bit about Pascal's principle. A nurse applies a force of about 4.4 newtons to the piston of a syringe in order to inject fluid. The piston has an area of 5 times 10 negative 5th square meters. What is the pressure increase in the fluid within the syringe? So we know pressure is equal to force per unit area. So this is 4.40 newtons divided by 5 times 10 to the negative 5th, and that's the area, 5 times 10 to the negative 5th meters squared. So here we end up with 88,000 pascals. That's all there is to that one. Next one's pretty easy too. Now we're looking at the effect of gravity on fluid pressure. And so we know that the pressure that you can find, the overall pressure, is equal to the atmospheric pressure plus the gauge pressure, which is rho g d or rho gh. A couple ways to write that. Here we're going to use the real value for pressure, atmospheric pressure. It's 101,325 pascals, so that's a little more precise. Plus, we've got 1,025 is the density of seawater. We're going to multiply that times 10, and then finally times 10 again. When you do that, you should get 203,825 pascals. And let's go ahead and convert this one over to atmosphere so we can see what that would be. We know that 1 atmosphere is about 101,325 pascals. And when you're done, you're going to end up with 2.01 atmospheres. So it's about twice the atmospheric pressure. For number 18, this one's kind of cool. You've got a giraffe, and the giraffe's brain is approximately 3.4 meters above its heart. They want to know what is the gauge pressure. So we just want rho GH. We just want rho GH for gauge pressure that its heart must produce to move blood to its brain. Ignore any effects of the blood flow through the arteries in a different area and assume it's identical, that the giraffe blood is identical to human blood. So the density here of the blood is going to be about 1,080 kilograms per cubic meter. So gauge pressure, PG, is equal to rho times G times H, or you could do D for depth, but here we're going to do height since it's a giraffe. Density of blood is about 1,080, gravity here is 10, and then it's 3.4 meters above its heart. So when we're done, we have 36,720 pascals. Next question says, how high can you suck water up a straw? The pressure in the lungs can be reduced to about 10 kilopascal below atmospheric pressure. So we're going to use our equation again. Pressure is equal to atmospheric pressure plus rho GH. And so if I took atmospheric pressure minus the total pressure, that would give me negative rho GH. So now we're going to end up with the difference between the two. So the pressure in the lungs is reduced to about 10,000 pascals. So this is 10,000. So we reduced it down to that. So that's our difference. And this is equal to negative. The density of water is 1,000, and then we have 10, and then we have H. So this would be measuring from top down, I think, is essentially what they're doing here. So this would be equal to 1 meter. That'd be your absolute value. And that is number 19. Let's go ahead and take a look at the next one, which is number 21. We have, in number 21, it says a sperm whale can reach depths of 2,500 meters. That's really deep below the surface of the ocean. What is the pressure on the whale's skin at that depth, assuming the density of seawater is constant from the surface to that depth, which it probably is not, but we're going to assume it. So the pressure will be equal to the atmospheric pressure plus rho G times the depth, or the height here. So this is 101. We'll use 300 this time, plus, and then we're going to do 1025 for the density of seawater, times 10 for gravity, and then our depth here is 2,500, or the height from the sea level surface down to where that whale is. When you're done, you're going to end up with 25,726,325 pascals, so an enormous amount of pressure. The next question is the maximum pressure on most organisms can survive is about 1,000 times atmospheric pressure. Only small, simple organisms such as tadpoles and bacteria can survive such high pressures. What then is the maximum depth that we could dive down to in order to kind of see what that pressure would be? So we've got 1,000 times atmospheric pressure. So the first thing we probably need to do is take 1,000 atmospheres, and we need to convert that into pascals. So that's 1 atmosphere is about 101,300 pascals. And so here you're getting about 101,300,000, so 101,300,000 pascals. The change in pressure then should be equal to rho GH. We've got 101,300,000 is equal to 1025 times gravity, which is 10, times that depth that we're looking for. And if you solve, you'll end up with 9883 meters. Measuring pressure is the next section. On this one, it says estimate the average blood pressure in a person's foot if the foot is 1.37 meters below the aorta, where the average blood pressure is about 104 millimeters of mercury. For the purposes, we're going to assume blood isn't flowing, which would not be good, but that's what we're going to need to do. So here the pressure is equal to the pressure on the aorta plus rho GH. So this is a closed system, so that's what we're going to need to use. This is 144 millimeters of mercury. We're going to add that to rho, which is about 1060 times 10. and then we have 1.37 meters. Now remember, this will give you an answer in pascals, and we can't add millimeters of mercury in pascals, so we need to do a conversion for this one thing. So we're going to multiply this, whatever we get here for the product there, times 760 millimeters of mercury. Oops, almost right, M. So mercury, all divided by 101,325 pascals. So if you do that, you should end up with about 213 millimeters of mercury. So a pretty simple problem to do. For number 29, this will be the last one we do before we go to another video on the buoyant force. So this one says a woman's systolic blood pressure when resting is 160. What is that pressure then in pascals, pounds per square inch, atmospheres, and torr? So each one of these we're always going to start with the given, which is 160 millimeters. I'm failing on this one. Here we go. Millimeters of mercury. And we know that there are 101,325 pascals in 1 and 760 millimeters of mercury. So that'd be 1 atmosphere. So that's the easiest way to do it, is to use what we know. So we're going to end up here with 21,322 pascals. For letter B, we have 160 millimeters of mercury. We're going to take this one and convert to pounds per square inch. So that's 14.70 pounds per square inch and 760 millimeters of mercury. And that will be 3.1 pounds per square inch. So obviously it's not huge. Think about your tires in your car, somewhere around 30, 32. If you have a bicycle, nice bicycle, probably about 100 pounds per square inch. For letter C, this is 160 millimeters of mercury. We're trying this time to go to atmospheres, so 760 millimeters of mercury, and yay, here's our 1 atmosphere. This is what we're basing everything off of. That's why you see numbers on the top and the bottom for each one of these that are not 1. And this will be equal to 0.21 atmospheres. For letter D, we're going to start with 160 millimeters of mercury. And we're going to go to torr. What's interesting is 760 torr is equal to 760 millimeters of mercury. So you really didn't have to do all this, but it does prove the point. And so this is 160 torr. And that is the end of the first video in the first section of the problems for fluids.